All right, let's go ahead and get it going this morning. So before we get started, does anyone have a question, comment, or concern about anything related to the class? Everyone get project 1 turned in okay? Can't be too simple, man. You could solve it in what, about 5 lines. Does anyone want to see the 5-line solution to the project? No. It's too soon. Yeah, man, if it works, it's all good. Here, we'll do that. That'll be fun. And pull up VS Code real fast. I'll show you. Oh, I feel like we were helping Esteban with his project. Let's close that. And let's create a new file. Let's save it on desktop. As project 1. Yeah, let's replace it. Okay. So here you go, man. Here's the, I think it's 5 lines. See, Nathan, I can do better than that. Check this out. Here we go. Line 1. Module. Top. Has what? A, B, C, and Y. Line 2 is the in module, or what'll be line 5. Ooh, maybe I can't. Maybe it takes 6. Input 3 to 0, A and B. Input, I lied. It's going to be 6 lines. Forget about C. Output reg 3 to 0, Y. Assign Y equals ternary operator C. Excuse me, C. Ternary operator. Then what? 1 is A minus B colon A plus B. There you go. And that's it. There's the 6-line solution to project number 1. And I don't think it can be made smaller than that. Oh, in fact, I screwed that up. I don't even need to make that a reg. There you go, man. Okay. So, any questions about that, by the way? So here's the thing, for those of you guys who are ultimately very salty at me right now, there is nothing in this that we didn't talk about in class at one point or another. So there you go. But hey, man, as long as the test bench passes, it's all good. If we want to unpack this just a little bit, yeah, don't be salty. So, I mean, we made, what, 4-bit inputs for A and B. We had our control input for C, our 4-bit input Y. We went over this in class, but we'll talk about it again. This is called the ternary operator. So basically what it says is Y is equal to, look at the value of C. If C is 1, assign A minus B. And if C is 0, assign A plus B. So the ternary operator is designed to replace, so an alternate way we could have done it would be to comment out these two lines, and you'd say output reg, you gotta make it a register for this next bit to work, Y, and then you have always at star, begin and end, and you say if C, then Y is equal to A minus B, else Y is equal to A plus B. So the ternary operator also exists, by the way, in other programming languages. It exists in C, it exists in C++, in Python. Basically, the ternary operator replaces this kind of structure, because this is such a common programming pattern that they gave it its own sort of syntax. So there we go. All right, any other questions about any of that? There you go. There's our 6-line solution to our first project. All right, so let us put that away and talk about what we want to talk about today, which is shift registers. All right, so shift registers. This is what I believe section 12.3 from the textbook, possibly. And here's an overview of what we're going to talk about. We're going to talk about right shift registers. Basically, we're going to work through several examples of just kind of unpacking. It's going to be basically the same as the register stuff that we talked about last time. I know this is the 11 o'clock class where we didn't have the lecture, so hopefully you sat in at 1 o'clock or you've seen the lecture on YouTube by now. Otherwise, some of this might not make much sense. But here we go. We're just going to jump right in. We're talking about right shift registers. We're talking about an 8-bit serial in, serial out shift register, a parallel in, parallel out shift register, the operation of a shift register, timing diagrams for shift registers, shift register with inverted feedback, and a general shift register counter. So let's jump right in. So the right shift register, we're going to shift bits to the right. And here's what that looks like. Let's go ahead and just sort of unpack what we got. So we have serial in here on the left side. We got serial out here on the right side. And then notice that we have 4 of these regular D flip-flops with a clock enable. And they're all attached in series, which is to say the output of Q3 goes to the input of 2, the output of 2 goes to the input of 1, the output of 1 goes to the input of 0, and the output of 0 gets spit out as output. And then down here, we've got shift and clock. We're already familiar with clock. By the way, what kind of edge-triggered flip-flop is this?
Rising.
Yeah, it's rising edge, right? There's no dot, so that's a rising edge. And shift attached to clock enable means that basically we can sort of start and stop the shifting operation, right? When shift is equal to 0, nothing happens. When shift is equal to 1, then on those clock cycles, the bits are going to shift. So basically, if we give it a 0 here, then that 0 will sort of just walk on every clock cycle. It'll jump from one flip-flop to the next. Let's take a look at the timing diagram and see what that looks like. So here up the top, we've got our clock signal, right? Things are happening on the rising edge. We've got our serial in. Here, this is the signal we actually want to put into the shift register. And then we have Q3, 2, 1, 0. So let's take a look at the beginning, that first rising edge, right? We're going to dump the value that's at input into the first shift register, Q3, right? So a 1 is going to get dropped here, you know, after some propagation delay, of course, and it's going to stay there forever. So notice that Q3 is going to be it's going to lag behind whatever the input is by 1 clock cycle, right? So here when it goes to, so it's still at 1, it goes there. Here when serial in goes to 0, it's going to wait until the next rising edge of the clock to do that transition to 0. So everything is going to be shifted over by 1 clock cycle. And then Q2 is going to be, let's see, it starts here at 1, and then at the first rising edge, it's going to look and say, all right, well, what was Q3? Well, Q3 was 0, so I'm going to drop down to 0. And then on the next clock, right, it's always going to look to the register, the flip-flop above it. So here at the next rising edge, it's going to say, all right, well, what was Q3? Q3 was 1, so now I'm going to go to 1. And then here at the next rising edge, it's going to say, all right, well, what was it? It was 1. All right, well, cool, I'm going to stay at 1. And then here it's going to go to the next rising edge and say, well, what is it? It's 0. All right, I'm going to drop down to 0. And same thing for Q1 and Q0, right? Q1 here at the rising edge is going to say, all right, it's 1, and then go to 1, and so on and so forth, right? Every register is just going to look back at every rising edge and say, hey, what was the input, or what was the value on that Q? And that's what we're going to pick up and move on, right? Provided that shift is enabled. If shift is 0, then the clock enables are 0, and nothing happens. So that's our right shift register. Are there any questions about it? Nathan says rising edge is when the clock pulse changes from 0 to 1, and that acts as a trigger for the circuit. You're absolutely correct. Any other questions about the right shift register? Because that wasn't really a question. Cody is typing. Cody says, never mind. So I thought I could get you if I said your name while you were typing. It forced you to ask the question. All right, let's move on to the next thing. Let's look at an 8-bit serial in, serial out shift register. As we're going to see, it's basically exactly the same as what we just looked at, but it's going to be a little bit different. When we draw the block diagram in broad strokes, we can just use a pretty simple, block symbol for this. We've got serial in, we've got serial out, and then we've got a clock that's driving the whole thing, right? And again, no dot means that this shift register is going to shift on the rising edge of the clock. So if we jump in and take a look and see what do we've got. So notice here that this is a little bit different than what we had before. This example actually uses the SR flip-flop. SR flip-flops. Which is an interesting choice for this shift register, but you'll see SR flip-flops used a lot in shift registers for a reason that we'll see here in a little bit. But notice that that does require us to take the serial in input and pass it through an inverter to go to R, right? Because we got to make sure that S and R are complementary to each other, right? That they're never equal to each other. So we've got to add that inverter there. And then from here, it's basically the same, right? There's Q7, 6, 5, 4, 3, 2, 1, and 0 all the way down. There's no clock enable here, so once it starts going, it just keeps going. On the rising edge of the clock, those bits are just going to jump all the way through the shift register and then spit out the end. So let's take a look at the timing diagram and see what that looks like. Right, we're only concerned now with serial in and serial out. So we've got our clock, it's running, it's doing its thing. We're triggering on the rising edge. So notice that since it's an 8-bit serial in, serial out shift register, that from the very first rising edge that had a 1, right, we've got this pattern here, this sort of, 1 and then a couple zeros and a couple ones and then some zeros. The take-home message here is that it's going to take 1 minus the number of bits, that many clock cycles to trigger. So from the very first one, it's going to be 1, 2, 3, 4, 5, 6, 7 clock cycles until that signal appears on the output, right? Because it's got to sort of trickle through all of the shift register before it spits out on the end, right? And then once it starts, then it's basically going to mirror what the input was, right? So we get the exact same pattern that comes out on the in there, minus a little bit of delay, right? And that delay, of course, is going to be 1 minus, if it's an 8-bit shift register, then it's going to take 7 clock pulses to get that output, right? You get that first one for free. So, any questions about the 8-bit serial in, serial out shift register? All right, well, let's keep it going. So let's now take a look at a parallel in, parallel out shift register, right? So the serial in means everything is connected in serial, right? We have one input or one bit that goes in, and we got one bit that comes out of the output. But in the parallel, all the bits can come in and all the bits can go out. So we've got down here on the bottom, parallel input. Still we're working with 4 bits, right? D3 through D0, that's parallel input. And then we have a parallel output, Q3, Q2, Q1, Q0, right? But notice the last one can also be a serial out, right? Because that last bit is going to contain the bits as we shift them through. You can use the last bit as a serial out, but you have the option of grabbing everything that's in the register all at once if you want. And we've got a couple of control inputs here. We've got serial in, of course, that we can pass data in a serial way. So I guess this is also a data input. So we just have 3 control inputs. Shift enable we've already seen, and then load enable, we'll talk about what that does. And then clock, notice here in this example, we got the dot or the bubble on the clock input. That means that this is going to be a negative or a falling edge. Shift register. So let's unpack it and see what we've got going on. All right, so as you can see, this one is a little bit more complex than what we originally had. So, and primarily because we've added the mux. But let's come back to the mux in just a second. Let's notice the important things. First off, we have serial in. We also have our parallel inputs, D3 through D0. And then we've tapped onto Qs, Q3, Q2, Q1, and Q0. And then now we've got this multiplexer that's going to tie as its control inputs to shift enable at the sort of 1, 0 there, and then load enable at the 1. So what shift does is shift makes the shifting happen, right? We're going to shift the bits down, and then the load says, well, what if we just want to dump everything into that shift register? So a couple of things as we go through each of these multiplexer steps one at a time is that the flip-flops are always running. There's no clock enable here. So the clock is always churning, and so the flip-flops are always updating. And so what we really have to do is just control what happens when the flip-flops update. And that's where this multiplexer comes in. So for the case 0, 0, so let's write that out. Case 0, 0, this is where SH is equal to 0, and load enable is equal to 0. And so what that says is, well, we don't want to shift and we don't want to load anything. So basically we don't want any movement. We don't want our register to change. And that's why the 0, 0 case of our multiplexer is tied to the output, right? So the output Q comes back around to the mux. And so when the multiplexer is getting a 0, 0, when we get that case 0, 0, then the output just feeds back into the input. And this happens for all of the flip-flops in the register. So this means that when we have 0, 0, shift is 0, load enable is 0, then we're just going to keep feeding the output of the flip-flop back to itself, and it will never update. Now let's talk about case number 1, or case 0, 1. So this is where shift is equal to 0, but load enable is equal to 1. So now we want to load the values into the register, and you can see that that works out here because the the parallel input, the D input, is tied to that 0, 1 case. So is D2 tied to 0, 1, D1 is tied there, and D0 is tied there. So whenever we have a 0, 1 on the multiplexer, well, then we're going to grab that parallel data and feed that to each of our flip-flops. Now let's look at, let me write it down here, case 1, 0. So this is the case where shift is equal to 0, but load is equal to, or excuse me, shift is equal to 1 and load is equal to 0. So this case, we want to actually do the shifting. So here we can see that, you know, SI, the serial enable, is tied to that case, the 1, 0. And so that's going to pass the output. And then the output of the, for everything else, the output Q is tied to 1, 0. So when we have 1, 0, it's just going to behave like that right shift register that we saw before, where the bits are going to be passed from one flip-flop to the next input and eventually to the output. And then the final case, case 1, 1, notice here, so that's when shift is equal 1 and load is equal 1. And this is sort of a nonsensical case. We don't want to shift and load at the same time. That really doesn't make any sense. So what they've done in this example is say, well, let's give shift precedence. So if shift is equal to 1, then we're just going to not care what load is equal to. So we've tied serial in to 1, 0 and also to 1, 1. And you can see that's happened here as well. All of the outputs of the flip-flops are tied to 1, 0 and also tied to 1, 1. So in the case where shift is 1, then load is effectively a don't care, and we're going to do a normal sort of shift operation. Any questions about that? That's going to be a fast class today. All right, so let's unpack that just a little bit and take a look at the shift register operation. And specifically, we're talking about this parallel in, parallel out shift register. So let's look at the state table. We've got our inputs, SH, and our load as our inputs. Then we have next state, Q3, Q2, Q1, Q0. So we're trying to come up with the characteristic equation for each of the flip-flops individually. So the first case here, 0, 0, right, is what we expected. There's no change, right? Q3 is just equal to Q3. None of the states change. In fact, they've listed it here as just this no change action. None of the states will update. Now we've got SH is 0 and load is 1. So now notice that Q3 is going to be taken from, or the Qs are going to be taken from the Ds, right? So we're going to load that parallel input into the next state, right? This is the load action. And then finally, like we already talked about, when shift is 1, load is effectively a don't care. And so Q3 is going to be whatever serial input is, and then Q2 is going to take from Q3, Q1 is going to take from Q2, and Q0 is going to take from Q1. This is our right shift case. So just kind of a recap of the operation that we had there. And then if we lay everything out as characteristic equations, then we don't even have to simplify it. Let's work out the first one, Q3 plus, right, is going to be equal to Q3 and SH prime and L prime, or D3 and SH prime and load, or SI and SH, right? No longer dependent on load enable for that one. So there's our first characteristic equation, or our characteristic equation for Q3. And if we look at all of the characteristic equations, we basically get the exact same structure. So if you were to implement this in Verilog, these are the equations that you would use. So any questions about that operation? All right, pretty straightforward. So let's move on and let's take a look at a timing diagram for this exact same shift register. So let's kind of unpack what's going on here, right? So we have our clock on the top, we have our load, we have our shift, and then here they've sort of tied some parallel values. We've said here D3, D1, D0 are just equal to this waveform. So when this is 1, what they're saying here is that we're loading a 1, 0, 1, 1. into the parallel input, right? Because D2 is going to stay at 0. So let's see what happens, right? The clock's running. The first thing that happens as, right, on the first rising edge. Ooh, actually, remember, if we go all the way back, these are falling edge flip-flops. So that's going to be important. So we're actually looking on the falling edges, right? So here on the falling edges, load is 1. And these are the load values. So you can see all the flip-flops on the falling edge, minus some delay, are going to be loaded with those values we expected. The 1, 0, 1, 1. And they're going to hang on to that, right? And we only want to keep load 1 for just one clock cycle, right? You only want to catch it for one piece. And then after that, as soon as the load goes to 0, we're going to start shifting through. And you can kind of see it start to walk, right? So shift is 1, doesn't matter what load is. Q3, this one is going to go down to Q2, down to Q1, down to Q0. This 0 that's at Q2 is going to walk down to Q1, down to Q0. This one at Q1 walks down to Q0. And then, of course, the value of Q0 just gets spit out as serial input. Let's see. And then notice here at the very end, they turn off the shift operation, which means that last value, that 1, is just going to hang out on that input, or excuse me, on that output, that Q output of Q0 forever. So we can see we loaded some values in using the parallel load, and then we sort of shifted them out. You're going to see this sort of structure comes up a lot in communications, right? So on an internet line or any wireless connection, basically any type of movement of information can only happen 1 bit at a time, right? Your fiber internet line can only shift 1 bit. Cody, I'll answer your question here in just a second. So a lot of times what you'll see is, but you might have 64-bit values. So what happens is those values get loaded in parallel into a shift register, and then they get pushed out one at a time. And as soon as the last one gets pushed out, we dump the next one in, and we shift those out one at a time. So we just sort of keep loading in parallel and then dumping out in serial. So at the end of really, like I said, any communications line, you're going to sort of take those values, put them in shift registers, and push them out one at a time. Cody asks, so after the shift operation, is the default value for each bit going to be 0? Yeah, well, that kind of depends entirely on like what is stored here. Notice that, let's see, as we shifted, there was that serial in output sort of hanging out there on the end. So they're sort of, I guess, assuming in this diagram that that's equal to 0, which is why after the first shift, Q3 goes to 0, and it's just going to be whatever that value is. So as you dump everything out, whatever is sitting on that shift input is going to be there. And in this case, it's 0. So yeah, so you can think of it as we wrote a value and we dumped out and we just have zeros left over. Or 1s. I've seen designs where they use 1s instead of 0s, kind of interchangeably. Yes, so if serial in were 1, then you would see them all default to 1 instead of 0. So they're going to default to whatever SI is. Okay, so let's take a look at a shift register with what they call inverted feedback. This is kind of interesting. So we've got a basic right shift register, right? Since we're going from left to right. We've got clock signals, no dot, no bubble, means that they're rising edge signals. And so we've passed from Q3 to Q2, Q2 to D1. And then notice instead of outputting Q, we've outputted the inverse back around. This is going to have an interesting effect of sort of looping us around. If we start with 0, 0, then there's a 0 on that last bit, which means that on the next clock, you're going to get a 1 on the first one. And then the 1 is just going to sort of walk through. As long as there's a 0 here, you're going to get a 1 on the first one. So notice that we kind of count up. We go 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1. And then we start walking our way back to 0. Right? So we start and we kind of walk around. This is basically what we would call, in fact, not basically, it is a counter. Now, it's not a counter that makes a whole lot of sense, but next time we're going to talk about counting circuits or counting registers, and the premise is fundamentally this, right? By changing the last value in the last flip-flop, we can sort of create this cyclic behavior where we sort of count around and then we go back to where we started, and we count around and we go back to where we started. Notice that we have this peculiar input. If we start it in a weird place, which isn't really possible, but 0, 1, 0, we end up just sort of like oscillating back between these two values. So by providing that inverted feedback, we're going to create a shift register that counts. And then next time we're going to see how using that effect we can create circuits that count, which is extremely, extremely useful. In fact, we'll generalize it before we pick up next time. So a general shift register counter has essentially a serial in and a clock, a shift register that is a number of bits. Those bits get spit out to some kind of logic, right? And this will affect what kind, let me write that out. This will affect what kind of counter we get, right? This could be a gray code counter, some kind of ASCII counter, something, whatever that counter is, right, is going to be provided in that feedback loop back to serial in. So we'll do much more detailed counters next time, but for now, are there any questions about this sort of general concept? Shift register to some kind of logic back as feedback to serial in makes counting happen. Cool. All right. In that case, that is it. We're not going to be quite done. We've got some extra time. But just to recap, we talked about right bit shift registers. We looked at an example of an 8-bit serial shift register. We looked at a parallel shift register. We sort of took it apart and unpacked it. We looked at its operation. We got its characteristic equations. We looked at the timing diagram for that shift register. And then we looked at inverted feedback and then kind of generalized that to say, well, this is kind of the basic general structure of a shift register counter. Any questions from the PowerPoint before we take a look at some Verilog stuff? All right, in that case, let's discard the annotations. Minimize that. Open. So let's take a look at implementing excuse me, some sequential logic in Verilog. All right, so let's make a module. Let's call it, here, I don't need the tablet anymore, the keyboard and the mouse. All right, let's take a look at this. Let's call it, I don't know, SEQ demo.v. All right. Let's give it a title here. So let's say demonstrate sequential logic patterns in Verilog. So let's define a module. Let's just call it top. And let's give it some stuff. Let's do, I don't know, I don't know what I want to do. Let's just do A and B. Should have thought ahead about what I wanted to do. All right. And module. In fact, let's illustrate this. Let's make a shift register. So we'll say let's do this. So let's say let's have SER in and SER out. And we'll call shift. And of course, we're going to need a clock in order to run everything. So let me expand on my demonstration here. Let's make an 8-bit write shift register. Alright, so like always, we need data inputs, we need control inputs, we need outputs, and we need some logic circuit. Alright, so let's say we're going to have an input. Let's make it 8 bits, so we're going to go 7 to 0. Oh, actually, we don't need that because we're just doing serial in. So let's say it's just 1 bit, SER in. Ooh, in fact, nothing needs to be that number of bits. Control inputs, we'll have an input shift. Semicolon, semicolon. Sorry if I pause, it's because I'm sort of making this up as I go. And I gotta think about what I'm doing. So our control inputs are clocked and our shift signal, and our output will just be SER out. Okay. And let's do this. We're gonna really confuse you. We're gonna need an output wire. Well, actually, we don't need to define it as a wire, I don't think. SER out. But now we actually need our shift register. So what I want to say is reg, this is what's going to be 8 bits, 7 is 0. Shift register. And let's go and implement our logic circuits. So just kind of recap that. We have our serial in input. We have our control inputs, clock and shift. We've got our outputs for serial out. We've got a register. That's 8 bits, an 8-bit shift register. And then what I'm going to say, first thing I need to do is I'm going to assign, I think this will work, SER out equal to shift register 0. So the very last bit of the shift register. Now what I want to do is I want to make this a positive edge triggered, so I'm going to say always at pos edge of the clock. So always at the rising edge of the clock, begin and end. And so what do I want to do? I want to sort of work backwards. I'm going to say shift register. Now there's some easier ways to do this, but we're going to sort of start with the most basic version. Shift register 0 is equal to shift register 1. Boom, just like that. Now let's notice this. I use this greater than or equal to sign. This is what's called a blocking assignment, right? If I just use a regular, remember that because Verilog isn't a programming language, it's going to try to do a bunch of stuff all at once. If I were to do it just like this, so that my next thing would be, you know, shift register 1 is equal to shift register 2. If I had, so this is what's called a blocking assignment. Without it, it's called a non-blocking assignment. So if I were to have it this way, I would actually have no control over which one of these occurred first, right? In your normal programming, you're used to, well, the thing that's at the top is going to happen first, and then we're going to go down the file. Well, that's actually not what happens in Verilog. Instead, these could happen in any order, right? Which is going to be problematic since I want to shift everything down. So I use this greater than or equal to sign to be a blocking assignment, and this says do this first and then go down to the next line, right? So it blocks and makes sure that everything happens in the proper order. So let's see, that's 1, 2, 3, 4, 5, 6, 7. Whoa, too much. 2, 3, 4, 5, 6, and 7. 1 takes from 2, and then 3, 4, 5, 6, 7, and then of course the last one here is going to take from SER in. Except I forgot one thing, didn't I? I forgot to include my input for shift enable. So what I need to do is actually I'm going to cut this out real fast. So I got to say if shift begin and end. Notice that I don't need to say if shift equals 1, right? Because it's just one bit. You know, this will be 1 or 0 on its own, and then I need to put that stuff back. All right, and there we go. There's our shift register. Are there any questions about what we built here before we go on to the test bench? Cool.
Do we need?
What's up?
Oh, sorry. Do we need to include the shift register in the module top?
No, because shift register is right here. I already defined it right there, right? And yes, so you remember that's a good question actually, because it illustrates a good point. The stuff up here is just the inputs and the outputs, right? Since the shift register that we've created here is not an input or an output, then there's really no need to include it up in here. You only need to include inputs and outputs. Internal stuff like wires or registers, you don't have to include in that. Did that answer your question?
Yeah, thank you.
No problem. All right, let's go ahead and test bench this. Now I didn't try this out ahead of time. I'm just kind of making this up as I go, so you may get to see me debug a little bit, but that wouldn't be the worst thing in the world. Timescale 1 nanosecond to 100 picoseconds. I want to include seq demo.v. Now my module seq demo underscore tb. End module. All right. Data inputs. Control inputs. Outputs. Unit under test. And then of course my logic simulation. This is just a habit. I know this is kind of unnecessary, but that's like just a habit I'm in as a programmer. I like to lay out everything that I'm going to do before I do it. So let's see. Here we're going to say reg ser in reg shift reg clock. Our output wire ser out. Unit under test seq demo ut. And then what do we have? I'm just going to copy this. SER in, SER out, shift, and clock. Now, one thing we want to do is we don't want to have to sort of toggle the clock all the time. What we want to do is kind of set the clock running and leave it alone. So what I'm going to do here is say always begin and end. And actually, the first thing I need to do is set clock equal to 0. And in fact, I'll set shift equal to 0 as well. So here, what I'm going to say is clock equals not clock, and then I'm going to delay for just 5. And that's all I need to do here. This just runs the clock at a period of, so it'll toggle every 5 nanoseconds, so every 10 nanoseconds is my clock period now. And now the actual simulation, initial, begin, and end. And all the stuff we're used to, right? Dump file. I'm going to do it on time. seq demo.bcd. Dump vars 0 seq demo underscore tb. Finish. And then let's be kind of simple. I'm just going to do this. I'm going to set ser in equal to 1. And then I'm going to set well, here, I'll delay for like 20. And then I'll say shift is equal to 1. So we should start shifting. And then I'm going to wait for, let's wait for 50 nanoseconds, right, to get it some time to sort of toggle through. And then I'll say shift equals 0 and delay for 20. Set SER in equal to 0. Delay for 20. Set shift equal to 1. And let's delay for 100, right? So all I want to do here is set a 1 on serial in, start the shifting, wait for about 5 periods of the clock, then set shift equal to 0. I'm going to wait for 20 periods, set serial in, wait for 20 periods. So basically we're just going to sort of see that it's stopping and it's operating, and then set shift equal to 1 and sort of see it run itself out. Are there any questions about what we've written before we see if it actually works or not? I'm like 85% sure this is going to work. All right, in that case, let's do the thing. So I verilog option O seq demo.vvp seq demo underscore tb.v. Oop. 3 unknown module type seq. Oh, it's because I called it top. Top. Let's try again. All right, now we got some stuff. SEQ demo at line 4. Port serial out 2 of module top has no direction declaration.
I think it's ser in and ser out. Sometimes you capitalize the in and out.
Ooh, maybe you're right. SER out. SER in. So what did it say? It said line 4. Oh, you're right. I did. I was inconsistent. Or actually, let me do it that way. SER out. Okay. So yeah, so there's a bit of a typo there. Let's run that and see what happens. All right, at 20 test bench 17, SER in is declared here as a wire.
Reg.
Yeah, I did it again, man. I did it for all of these. Oh. That's what happens. This is why it's important to agree on a convention for yourself. All right, one at a time. So that means I need to change. At line 32. Yeah. All right, there we go. So my stupid typos aside, now we say VVP seq demo.vvp. Got 1 minute left. And again, it helps if you use the right command. There we go. GTK wave seq demo.vcd. Let's see if we got lucky, man. We won't have time to debug it. All right, so we've got stuff. And let's say, look at that. So we've got clock. The clock runs. That's nice. Serial in was set at 1 for a long time, and then went to 0. And then we set shift out. So check this out. Notice that serial out doesn't appear until it's basically undefined until it comes here, and then it sort of stays that way forever. If we want to pop it open and take a look at what we've got, so if I go down and select UUT, I can grab the shift register itself and append to that. Notice that it starts, looks like it's sort of doing some stuff, and then it gets kind of weird. Let's open it up and say, hey, look at that. That is pretty good, except, oh, that's where we stopped. So look at this. This might be kind of confusing to look at, but shift starts, the shift register, the first bit takes the first value. It's a 1 from our serial in. And then notice at every clock cycle, it starts walking its way down. And then here is where we went to 0. We paused the shifting for a time, and then we turned it back on again, and we sort of shifted all the way out. So the very last thing here is that, so then serial out, notice, is the same as shift register 0. So tick, 1, so 1, 2, 3, 4, 5, delay 6, 7, 8 ticks for our serial out value to appear there on the output. And there we go, man. We got it right. It's working. And then notice that the 0 starts walking in from when we turned serial into 0. So, all right. And there we go, man. That's shift register. That is doing some sequential logic in Verilog. Are there any questions? Your project number 2 is not as sophisticated as this. It's still sequential logic up to some of these concepts, but actually it's much easier than this. So it's 11:51. Any questions, comments, concerns before we say goodbye until Friday? I think there's people signing out of the chat already. All right. Well, in that case, have a good rest of your day. I've got office hours from 3 to 5 today if you have any questions, but since there's nothing due, I suspect I won't see anybody. But I'll see you guys on Friday. Thank you.